All right, hello everybody. This video is going over Unit 1, Lesson 3 of the AP Chemistry curriculum. We are going to be talking about elemental composition of pure substances, and today's learning objective is to explain the quantitative relationship between the elemental composition by mass and the empirical formula of a pure substance. So some substances are made up of molecules, while others are made up of atoms or ions that are bonded together in set ratios. The law of definite proportions says that a compound always has the same ratio of elements by mass, and the empirical formula shows the simplest whole number ratio of those atoms in the compound. So these are just the different types of empirical formula questions that will show up on your AP exam at the end of the year. The first type is when you are given the mass or percent composition data of the elements within a compound, and then you'll have to solve for the empirical formula. You can also do combustion analysis when you have a sample that's burned in oxygen gas, and you're going to analyze the products to determine the amounts of carbon and the amounts of hydrogen. And then finally, we do hydrate analysis. So essentially, you're heating a hydrated ionic solid, and then you're going to analyze the mass change so that you can get your moles of water, and that way you can figure out the formula of your hydrate. So all pure substances have a fixed composition. Remember, pure substances are going to be elements or compounds in fixed ratios. This means that elements present and the ratio of those elements is going to be the same for every single sample of the compound. So for example, when we have water, water is always made up of 2 hydrogen atoms for every 1 oxygen atom, no matter where the sample comes from. It's always the same quote-unquote recipe. The empirical formula is the lowest whole number ratio of atoms of the element in a compound. To get the empirical formula when you're given percent composition or mass, I always like to use the jingle percent to mass, mass to mole, divide by small, multiply to whole. So let's go ahead and do an example of this because we did learn this in pre-IB, but I just want to make sure it's solidified because we do use it quite often. So the first part of our jingle is percent to mass. We are already given the mass, so we don't actually have to do that step. So I always start with what I have, which is 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. So the next step is going to mass to mole. So if we want to go from mass to mole, we're going to divide by the molar mass, because we know in 1 mole of anything, it's going to be equal to the molar mass of that same thing. And remember, the molar mass is from your periodic table. So for calcium, we have 40.08. For every 1 mole of oxygen, we have 16 grams of oxygen. And for every 1 mole of hydrogen, we have 1.008 grams of hydrogen. So go ahead and solve for those. So now that we have our moles, we're going to go ahead and divide by the smallest one. The smallest one is going to be calcium, so 0.3368. And these are both going to be about 2. And then the last step is multiply to whole. These are already whole numbers, so we do not have to do that step. So now we just have to write out the formula. We have 1 calcium, we have 2 oxygens, and we have 2 hydrogens. And I hope you remember the polyatomic ion hydroxide, because once you see this equal amounts of oxygen and hydrogen, you should just assume that it's together as hydroxide. So the answer to this one would be calcium hydroxide. All right, so let's practice turning these percent compositions into empirical formula. So when we are given percent composition, it's going to tell us how much of each element makes up 100% of the compound. So if we pretend that we have 100 grams of the compound, then the percentages directly become grams. So in the first example, 77.78% becomes 77.78 grams because we're assuming it's out of 100 grams. Now we can assume that because ratios don't change with the sample size. So because it's a ratio, it really doesn't matter what we put it out of. So we just put it out of 100 to make it easier in terms of math. So the first part of the jingle, remember, is percent to mass. So we have 77.78 grams of iron, and we have 22.22 grams of oxygen. The next part of this is mass to moles. So remember, to get to moles, we're going to divide by the molar mass. So in 1 mole of Fe, we have the molar mass of Fe, which is 55.85 grams. And in 1 mole of oxygen, we have 16 grams of oxygen from the periodic table. So when we do that math, we end up getting 1.39 for both. So when we divide it by the smallest, which is 1.3888, we're going to get 1 for each of those. And since they're already in whole numbers, we can just go ahead and assign the formula, which would be 1 iron and 1 oxygen. So now I want you to take the time to do 2 and 3 on your own and pause the video, and then once you play it, I will show you the key. And for numbers 2 and 3, we did not get whole numbers, so we did have to multiply until they were whole. So for number 2, we got 1 and 1.5. So in order to get rid of that 1.5, we had to multiply both of them by 2. And so we end up getting 2 irons and 3 oxygens. And then for number 3, we end up getting 1 and 1.3 repeating. So in order to get rid of that 0.3 repeating, we need to multiply by 3. So we multiply both by 3, we end up getting 3 irons and 4 oxygens. All right, which of the following are possible in empirical formulas? Remember, empirical formula is the simplest whole ratio. So these should be very easy to identify, and they're also pretty common on the multiple choice section of the AP Chem test. So CH cannot be divided down anymore, so that would be an empirical formula. Same with CH2. C4H4 could be simplified down to CH, so that is not an empirical formula. CH3O could not be simplified down. And then for number 5, C3H6O2, that also could not be simplified down. So those 4 could be considered empirical formulas because they are the simplest whole ratios of those atoms. All right, so again, we're going to take our percent compositions and turn them into empirical formulas. So the first one for part A, we have 15.8% carbon. And we know we can change the percent sign right to grams. And then we have 84.2 grams of sulfur. So our first step after converting it to grams is to convert it to moles. So we know if we want to go from grams to moles, we use 1 mole is equal to the molar mass. And we want the mass to be on the bottom so that our units cancel out and we're left with moles. So in 1 mole of carbon, that is equal to the molar mass of carbon from the periodic table. And in 1 mole of sulfur, that's also equal to the molar mass of sulfur from the periodic table. So now that we have our moles of each, we're going to divide it by the smallest number, which is 1.3156. And because we have 2 whole numbers, we can go ahead and just assign them to their empirical formula. So we have 1 carbon and 2 sulfurs. So that is our empirical formula. And now to do part B. Same thing, it's out of percent, so we know we can convert it right to grams because we're going to assume it's out of 100. So we have 40 grams of carbon, we have 6.7 grams of hydrogen, and we have 53.3 grams of oxygen. So first step is to convert those into moles by dividing by the molar mass. So in 1 mole of carbon, we have 12.01 grams. In 1 mole of hydrogen, we have 1.008 grams. And in 1 mole of oxygen, we have 16 grams. So now that we have our moles of each of our elements, we can go ahead and divide by the smallest one. In this case, it's both carbon and oxygen with 3.33056, which is going to give us 1, 1, and 2. And because they're already whole numbers, we can go ahead and just assign them. We have 1 carbon, we have 2 hydrogens, and then we have 1 oxygen. All right, a compound contains 1.1 moles of potassium, 0.55 moles of carbon, and 1.65 moles of oxygen. What is the empirical formula of this compound? So I love when we get these ones because it's just a little bit of a break from all of the steps. So we are already in moles, so all we have to do is divide by the smallest, which in this case is going to be 0.55. That gives us all whole numbers for our ratios, so we can go ahead and just assign them. So we have 2 potassiums, 1 carbon, and 3 oxygens. So the answer for this question would be C. Okay, so when substances have the same empirical formula, it doesn't mean that they have the same chemical properties. However, it does mean that they have the same composition. So for example, I don't know if you know what formaldehyde and glucose are. Glucose is a sugar and formaldehyde is essentially a preservative. Glucose is sugar, so we consume that on a normal basis. You cannot consume formaldehyde because it can be toxic to your body. So even though they have the same empirical formula, they are much different in terms of their chemical properties. Once the empirical formula has been established, you can calculate the molecular formula if you're given the right information. So the molecular formula is going to tell us exactly how many atoms of each element we have in our compound, rather than just the simplest whole ratio. So when we're solving for a molecular formula, you obviously need the empirical formula mass, and then you need the molecular formula mass, and that's going to give us an integer. And that integer is what we multiply by the empirical formula to get our molecular formula. A 10-gram sample of vitamin C was analyzed and found to contain 4.092 grams of carbon, 0.458 grams of hydrogen, and 5.45 grams of oxygen. Given that the molar mass of the compound is 176 grams, determine the molecular formula of vitamin C. So we're trying to find the molecular formula, but remember, we can't get the molecular formula unless we have the empirical formula. So our first step is to get the empirical formula. Now we're not given percent, we are given grams to begin with, so we're going to start with that. So we have 4.092 grams of carbon, we have 0.458 grams of hydrogen, and we have 5.45 grams of oxygen. So I'm going to divide those by their molar masses in order to get moles. So next step to solving for the empirical formula is dividing by the smallest, which would be 0.3406. And we do not have whole numbers, so we're going to multiply this by 3 to get rid of the decimals. If we multiply one thing by 3, we need to multiply them all by 3. So for our empirical formula, we get 3 carbons, 4 hydrogens and 3 oxygens. So this is our empirical formula. So now what it's asking us is to solve for the molecular formula. So in order to solve for the molecular formula, we're essentially going to be multiplying it by n, and we need to figure out what n is. So in order to figure out what n is, the actual formula is to have your molecular mass, which is going to always be given to you, divided by your empirical formula mass, which we just found the empirical formula. We just have to get the actual mass of that. So again, molecular mass is going to be given to you. That's at 176 grams. Now we need to solve for the molar mass of this empirical formula. So we're going to have 3 times 12.01 plus 4 times 1.008 plus 3 times 16. So solving for that gives us an empirical formula molar mass of 88.062. And when we solve for the integer, we end up giving 2 for our integer. So this here is our empirical formula. Our molecular formula is just that multiplied by 2. So we'll now have 6 carbons, we'll now have 8 hydrogens, and we'll now have 6 oxygens. So this would be our final answer for the molecular formula. So before we move on, I want to make sure that we can go backwards, and when we're given our molecular formula, we can actually get the percent composition as well. So essentially when I'm asking you for percent composition, I'm just asking you for the percent of each element within the compound. So when you're actually solving for it, it's just essentially the part over the whole. So if I want to look for the percent of nitrogen, I'm just going to put the mass of nitrogen over the mass of the entire compound. So let's go ahead and do that. So if I'm looking for percent nitrogen, I want the mass of nitrogen. I have 2 of them, so 2 times 14.01, divided by the mass of the entire compound. So I have 2 times 14.01 plus 4 times 16. That would be the molar mass of the entire compound. And then you're going to multiply it by 100. So that gives us 30.45% nitrogen. And then you could do the same thing for oxygen and put the amount of oxygen over the entire compound, or you can just subtract this number from 100. It doesn't matter, you'll get the same answer. Now we're going to talk about hydrates. So when I say something is a hydrate, that means it is bonded to a certain number of water molecules. So when I say that it is a hydrate, that means it's with water. When I say the word anhydrate, that means without water. So here we have calcium chloride dihydrate. Once you add heat to that, the water is obviously going to evaporate and come off of that calcium chloride, and you're left with calcium chloride and water molecules as a gas. With naming ionic hydrates, you're going to name your ionic compound the exact same, and then you're just going to follow that ionic name with the prefix of how many water molecules you have and hydrate. So for example, the one we did in the last slide was calcium chloride dihydrate because there were 2 hydrates attached to that calcium chloride. The one below that, lithium chloride, has 4 water molecules, so it would be lithium chloride tetrahydrate. And those are the same prefixes that you use for naming covalent molecules. So now let's go ahead and learn how to calculate a hydrate. So what you're going to do when you are dealing with calculating a hydrate is you're going to convert the mass of your sample without water and the water to moles. And then you're going to use the formula X equals the moles of water over the moles of your anhydrous compound to get the integer that goes in front of water. So let's start out with this question. A 0.386 gram sample of sodium sulfate hydrate with the general formula Na2SO4xH2O is heated. The mass after heating is 0.17 grams. What is the full formula and name of the hydrate salt? So in order to find out what X is, we have to get the moles of water and divide them by the moles of Na2SO4 without the water, or the anhydrous salt. So in order to actually solve for X, we need to convert our grams into moles. And right now we're given our grams of our hydrate, or with the water, and we're given our grams of our anhydrate, which is without the water. So we're already given the mass 0.17 grams of Na2SO4. So we can go ahead and convert that to moles and get our denominator for this question. So because we know that 1 mole is equal to the molar mass of that same thing, we can go ahead and divide 0.17 by the molar mass of sodium sulfate, and that will give us 0.0011968 moles of Na2SO4. So now we have the moles, which is going to go on the bottom of the equation in order to find X. We need to get the moles of water. So looking at the data given to us in the question, we started out with the mass of the hydrate, then we added heat to the sample and evaporated all the water, and then had the mass of just the anhydrate. So if we subtract the mass of the anhydrate from the mass of the hydrate, that's going to give us just the mass of the water that was taken out. Now we have our mass of water. We need to go ahead and convert that into moles of water. And we know in 1 mole of water, it's equal to the molar mass of water from the periodic table, which is 18.016 grams. So then in our calculator, we would be doing 0.216 divided by 18.016. That's going to give us 0.011989 moles of water. So now finally, we can go ahead and solve for that integer of X. So X, we're going to put our moles of water on top, 0.011989, over our moles of sodium sulfate, which is 0.0011968. And that's going to give us 10. So our integer is 10. So our formula, when we plug this in, would be Na2SO4 10, please hold, 10 H2O. And then to name that, it would be sodium sulfate decahydrate. And that would be your answer. Alright, so we're going to end our 1.3 lesson with one more example. It says some phosphorus is heated in air to produce phosphorus oxide. The following data was collected. Determine the empirical formula of phosphorus oxide. So in order to determine the empirical formula, we have to have either a percent composition or an actual mass of each of the elements in the compound to start with. And we are given data that has mass. So we just need to figure out what's the mass of the phosphorus and what's the mass of the oxygen. So if we look at these 3 sets of data, we have the mass of the crucible, we have the mass of the crucible and the phosphorus, and then we have the mass of the crucible and the phosphorus oxide. So what we can do first is get the mass of the phosphorus. And we will do that by taking 27.19 grams and subtracting the mass of the crucible. So that means in this sample we have 1.85 grams of phosphorus. So now we need to figure out how much oxygen was added into the phosphorus oxide. So by taking the mass of the crucible and the phosphorus oxide and subtracting the mass of the crucible, I get a mass of 4.24 for the entire compound. So then I will subtract 1.85 and that will give me 2.39 grams of just oxygen. So now I have my masses of each element within the compound. I can go ahead and follow that little jingle that we worked on at the beginning of the video. So we're already in mass. We need to convert to moles. we know that in 1 mole, it's equal to the molar mass of that same thing. So after dividing the molar mass of phosphorus, we get 0.059735 moles of phosphorus. And now we'll do the same thing for the oxygen. The next step is going to be dividing by the smallest number, which will be the 0.059735. And now since they are not whole numbers, we're going to multiply until they are. Since it's a 0.5, we need to multiply by 2, and whatever we do to one, we need to do to the other. So we'll have 2 moles of phosphorus and 5 moles of oxygen. So our empirical formula is going to be P2O5. All right, I hope this video helped you out. If you need any help, please do not hesitate to ask me. I hope you have a great day. Bye.